if I had a uniformly charged sphere, and this is a problem that we've looked at before, in the past we said, okay, we said that a uniformly charged sphere on the outside behaves as if it were a point charge, right? The electric field is the same. Well, where we can actually formally prove that, we could do it with a brute force sort of a calculation. We showed a demo program of this a while back where you broke the charge up into rings. But you could do the same thing with Gauss's law. And it is the exact same argument as with the point charge. If this is a uniformly charged positive sphere, and I'm drawing a Gaussian surface that is concentric with it, and I didn't quite draw it very well. Let's make it a little bit more concentric. So that this capital R is the radius of the sphere, and say little r is the radius of the Gaussian surface. You go through the same steps again. You say, okay, this is a very symmetric situation. I rotate the sphere, and if it's uniformly charged, no matter how I rotate it, it should look the same on all sides. So that tells me at a uniform distance away from the center, the electric field has got to be radially outward, and it's got to have the same magnitude everywhere on that surface. And then it just follows the exact same type of reasoning. The electric field is uniform. It's always perpendicular to the surface. The dot product just gives us the magnitude of the field. We can bring the magnitude of the field, the uniform field, outside of the integral. And then the integral we're taking just happens to add up to be the surface area of the sphere. And so we find again that the magnitude of the field times 4 pi r squared is equal to the charge inside over epsilon 0. And so you get the exact same result. You get a result that looks like the charge of or the field of a point charge for a uniformly charged sphere. Okay? So that's where that comes from. Okay, we're using Gauss's law to show that in a more formal way, that from the symmetry of the situation and from Gauss's law, it looks exactly the same as a point charge at the very center. Okay. Another proof we could do is, what if we were looking at a situation where our Gaussian sphere was, instead of being outside the uniformly charged sphere, what if it were inside? So this is, for example, a ping pong ball, okay, a hollow plastic shell that has a uniform positive charge on it. And our Gaussian sphere happens to be just beneath the surface, inside that ping pong ball. Well, let's apply Gauss's law. Again, E dot n hat dA is equal to Q inside over epsilon 0. How much charge is inside the Gaussian surface? None, right? Because all the charge is on the outer surface of the ping pong ball, and our mathematical surface happens to be below or inside this sphere. So there's no charge inside. That doesn't necessarily mean that the electric field is equal to 0, okay? Because we've seen cases where you might have a positive flux on one side and negative flux on the other, and it sums up to 0, but there is electric field. But again, you go back to the symmetry of the situation. No matter what direction or what angle I look at this sphere, it's got to look the same. The only way for it to be the same on all sides and give me a flux of 0 is for the electric field to be equal to 0. So inside the sphere, no matter how big this Gaussian surface is, we can imagine shrinking it down or expanding it out to just below the surface. The electric field inside a uniformly charged spherical shell, due to that shell, is equal to 0, okay, which is a result we knew from before, but now this is the more mathematical and elegant, formal way of proving it. Okay? So these types of proofs physicists like to use Gauss's law for. There is another thing that we can think about that we dealt with in the past. Which is the electric field inside a conductor. And we're dealing with the static equilibrium situation. So here is a piece of metal, and it can be any shape. I don't care. And it can even have some charge on the surface. And maybe even be polarized or something like that. And well, what we actually want to do is we actually want to prove, before I even draw those charges, we had said that any excess charge on a conductor has to be on the surface. Okay, we can't have any excess charge in the interior. And we just kind of hand waved around that and said, well, if we had any excess charge, the mobile charges would move and the charge would be on the surface. More formally, we could use Gauss's law and say that, let's think about a Gaussian surface that basically follows the outline or follows the shape of our piece of metal. But we're sort of just shrinking it just below the surface of the metal. Okay, so we have a Gaussian surface that kind of just is sort of barely underneath the outer skin of the metal. Now, we do know something about the net electric field inside a metal. At static equilibrium, it's got to be equal to what? 0. Okay. We don't need Gauss's law for that. That comes from, where does it come from? When did we, this is a review. When did we first talk about this? What relationship did we use to? Okay, the mobile electrons and the speed of the mobile electrons is related how to the electric field? U times E, right? U is what? Mobility, okay. So we have a metal with some mobility. If we're in static equilibrium, by definition, V is equal to what? 0. Okay, so if V is equal to 0, the electric field has got to be equal to 0. That we already knew. Once you know the electric field is 0, well, what's the flux through this surface if the electric field is 0? 0. So what's the charge inside? 0. So there can't be any excess charge inside. And if you imagine, again, mapping that surface to just below the surface of the metal, the only possible place the charge can be is outside of that surface. Okay. So there really isn't any mathematics involved in some sense. It's just knowing how the Gauss's law behaves and using this sort of geometric reasoning to figure this out. We can also use this to show something we haven't actually talked about before, which is this. What if you had a piece of metal and there's a hole in it? And I'm drawing this in cross section, but what I really have here is a shell. So imagine like just a silver hollow ball, okay, or just a shell of metal, and the interior is hollow, okay. And so this is metal, and this is just hollow inside. And so the question is, okay, we can't have any charge in this region. We've already shown that. Can we have any charge on this surface? So can I have maybe some positive charge here? Is that possible? How would we show it? We want to use Gauss's law. So what surface do I want to pick? The Gaussian surface where? Inside here, or? Okay, inside the metal, right? We want it sort of the surface to be in the interior of the metal, but outside of the hollow hole inside the metal. And again, the electric field is equal to what in the metal? It's got to be 0. So the electric flux has got to be, if the field is 0, the flux has got to be 0 also everywhere. And so the charge inside has got to be equal to 0. Okay? So we can't have any net charge on that inner surface. Now, that still doesn't get us the whole way through, though, because you could have maybe some negative here and some positive here, and so the interior is polarized, and this charge, negative charge, exactly cancel out this positive charge. That would satisfy Q inside being equal to 0. So Gauss's law can't tell us whether that's a possibility or not. But there is another principle we can use to figure this out. Any ideas? We've seen it before. If this were possible, what would I have inside this hollow cavity? I'd have a dipole, and so if there's a dipole, there's got to be what? If I could measure electric field, and the electric field would be pointing what direction? Positive and negative. Okay, so there's an electric field in here. Electric field is equal to 0 out here. Does that cause a problem? What about potential difference? If I go from here to here in the direction of the electric field, the potential difference is going to be what? It's going to decrease. So I get a net delta V that is negative, right? Well, is that the only path I could choose? No. What other path could I choose? Through the metal. What if I choose a path through the metal? That delta V's got to be what? 0. Is there a problem here? It doesn't cancel out, right? The round trip potential difference has got to be what? 0. And so if I go through the metal here and get a 0 potential difference, I better go through here and get a 0 potential difference. So combining Gauss's law with delta V round trip equal to 0 tells us a hollow cavity inside a metal at static equilibrium actually can't have any charge on it. The only charge can be on the outer surface, not on the inner surface. Okay? Even if it's polarized, still get a 0 charge on the inner cavity. Okay? Which is kind of useful, because here's a question. You're in a car when a thunderstorm approaches. You see a lightning strike nearby. What should you do? "100% say stay in the car, all right." First time ever. First time ever. Now, based on this, can you answer why you should stay in the car? Because you're in an enclosed metal box, and inside here there's going to be no net charge, and therefore the electric field inside here is going to be equal to 0. Yeah, you actually have, and a metal frame of a car isn't completely enclosed, right? But it's actually close enough. It's actually close enough between the roof and the supports, the frame underneath. It almost obeys this law, even if you have like a cage or something that seems open and it isn't a completely closed surface. If you can get close enough to a kind of a closed cage, then you've essentially made, sometimes it's called a Faraday cage, a metal box where the net electric field, even if there's charge on the outside, okay, or a lightning strike, you're staying relatively safe. It's not due to the rubber tires insulating you or anything like that. It's basically due to the metal frame of the material.